Okay, it was mentioned that we have to supply to the winding, the rotor winding field with the static or fixed poles of your field. Means that if you take a look at the slide or the YouTube, we have here the windings which provide with the positive and negative terminal poles and terminal voltage, positive and negative. So these positive and negative poles or negative terminals we have to fix, even though the rotor is rotating. So we have to fix it, and we fix this terminal as positive, this terminal as negative, all the way of the operation. Means that we have to supply the power from external DC source to the rotor by means of slip rings and brushes. So we have to provide slip rings such that the positive maintain positive, negative maintain negative. Or by the second way is by supplying the DC power from a special power source mounted directly to the shaft of the generator. Means that we put the source on the shaft itself. The source will rotate together with the poles here, and or we put the DC source somewhere else. We connect the DC source to the coils with the slip rings. So that's two ways of how to connect the source to the magnetic field terminal. So on the larger synchronous machine, the brushless exciter, we call brushless exciter, are used to supply the DC field to the machines. So this brushless exciter is just like a small AC generator with its field circuit mounted on the stator and the armature circuit mounted on the rotor, the shaft of the rotor. So this is the figure or the example of the two-pole wound rotor generator and their exciter. This is their exciter, which provide the DC to the internal rotation field of the generator. So this is the shaft. This is cross section of the large turbo generator, the non-sailing pole kind of generator. Stator here, rotor, cooling ducts. So we can see the construction is longer compared to the diameter of the machine. So this is rotor block of the larger or the generator, and we have a pole face slot for ventilation. Also this one, the non-sailing pole. This is the shaft. DC current terminals, we keep it positive as positive, negative as negative. Meanwhile, this is the sailing pole type, and you can see the just like a disc. So this one for large hydro generator. This one is your stator part, and generator stator. So you can see the sailing pole construction. It will be slotted. The rotor will be slotted into the stator. So this is the rotor support with the turbine and generator bearing. Okay, this is not your attendance lah. This is the previous attendance. So now we are talking about the generator. So we are following the Fleming's right hand rules for generators. Meanwhile, if we are referring to motor, we use the left hand rule. So this is right hand rules. Okay, this is a slip ring that like I mentioned to you before. So for generator, this is not your load, this is your source. And so we turn this is the shaft. So we mechanically turn the shaft, the rotor, so the coil will turn as well. Let's say we are turning to the clockwise and clockwise, right side. So we can see this is considered as zero reference. At zero reference, so the flux does not cut and the magnetic field. So we have zero, and zero current measured on the terminals. The terminals means that at your load. Okay. So when we turn to the maximum cutting point, which is 90%, 90 degrees, sorry, 90 degrees, we turn to the 90 degrees, so this is maximum cutting point, so we produce the maximum voltage and also maximum current to the terminal, and we can measure here. And then another 180 degrees, so it will be perpendicular to the flux, so we have zero voltage and zero current. And then another maximum conduction angle of 270 degrees, so we have maximum voltage and current but in the other direction. Then we turn back to zero. So this is the principle of how the generated voltage and current of the synchronous generator. Okay. So the instantaneous voltage induced VI means that the at this any of this rate point is equal to Vmax times sine theta. So at any angle here, theta, from 0 to 360 degree times your Vmax, and so that is the amount of your dot here. So this is instantaneous induced voltage. Vmax is the maximum induced voltage here. You have Vmax. The angle of conductor rotation from 0 to reference, from 0 to 360 degree. So if we pick, or we have the theta at 180 degrees, so Vmax times sine theta becomes, sine theta is 0, so we have a 0 voltage produced at this point. Meanwhile, if we have a theta at 90 degrees, so we produce sine theta of 1, so V instantaneous induced voltage is equal to Vmax. If we have three-phase synchronous generator, so the poles will be distributed evenly, phase A, B, and C. And so we have here three-phase generator. At least we have 6 poles, and phase A, pole B, and pole C. And so pole A, B, and C represent the beginnings, A dot, B dot, and C dot here, beginning of each phase windings. Okay, in terms of speed, same like previous induction motor or machine speed. So mechanical speed equal to 120 times your electrical field frequency divided by number of poles. So if you take the F up here, so it becomes N divided by 120 and times P. And so that's your generated frequency. How many poles you put in, how many turns you apply, or frequency, the speed you apply, and so it produces the frequency of the generated electrical frequency to the grid. So this is the internal generated voltage EA, and depends on the constant and also the mechanical radiance of your system. So the voltage depends on the flux of the machine. The higher the flux, so the higher the generated voltage will be, and also the frequency of the speed of rotation. And in the machine construction means that the materials, the fineness of the construction, the higher coupling of the system, and the better the coupling, the higher the generated voltage here. So F is your distribution, flux distribution. N is the number of conductors. The higher conductor you use, the higher the EA will be generated. But the number of conductor will be limited by the thickness of the conductor. The thicker the conductor, you cannot wind any much more, and so it will be a pro and cons over there. So this is the equivalent circuit of your synchronous generator. It's almost the same like the separately excited DC motor or DC generator we discussed in the DC machine. So EA is not usually the voltage that appears at the terminals of the generator. EA is here, internet generator, but we have to minus the series resistance and impedance. That then we can measure the V phase here. So the VT is not EA and VT is here, V phase. What is EA is the internal generated voltage, and before your RAN and X as here, series impedance and series resistance. So there are many factors that cause the difference between internal generated voltage and output voltage here. Depends on the first, we have four main contributing factors, which one of it is the distortion of the air gap magnetic field by the current flow in the stator, which so-called armature reaction, and then we will also affected by the self inductance of the armature coils, and X1 or XA here, and also the stator resistance of the armature coils, and also the effect of the selling pole rotor shape and the construction kind of system, how we construct, and the core construction. But this one is ignored due to the minor error compared to the non-selling poles. So these three factor or affecting factor will be discussed accordingly.